Thank you. So, yeah, thank you for the introduction, and yeah, I hope you get some good food, and yeah, I have the task to keep you updated, and yeah, so today I will discuss about the microcontrollers called the Geckos from Silicon Labs, and yeah, it should be fun. I hope you will enjoy. So 2 words about me. I'm security researchers. You can check my website. There is some previous results, of course, in display. So no affiliations, and my main focus it's focusing on hardware vulnerabilities and the reverse of embedded devices. So today we are going to discuss about hardware security. So I will present the targets. I will give details about some preparations, of course, and I hope you will follow my hacking journey. And normally we will see what are the results, I will say. So what is Gecko? Gecko is the short name for the Silicon Labs EFM32. It's quite popular platforms released in 2010, and you can find these platforms in a lot of different embedded products. For example, here it's EFM32 GG, so giant gecko in a Fitbit Surge, which is how can I say that? A fitness watch, typically. So, and there is a lot of EFM32 based products out there. So I hope this talk will push you to investigate a little bit on all these different devices. So, about the company, it's Silicon Labs. It's a US semiconductor company. They focus on ultra low power MCUs and wireless SoC. It's a big company. It's Nasdaq company, and they focus typically on smart metering, all objects related to health and fitness, IoT, home automation, industrial stuff, etc. So, and about the Geckos, they were designed originally by another company called Energy Micro. It's a Norwegian company. And in 2013, they were bought by this American company. So typically, we have 9 different Geckos. And depending on their capabilities, they can be based on ARM Cortex, M0, M3, M4, and the size of the flash and the available RAM and some peripherals can be different depending on the platform you choose to develop your product. And what's interesting is the longevity commitment for the oldest one is March 2026. So we can expect to see them on the market during a couple of years, and even until 2030. So it's quite an interesting target. So typically on embedded devices, the classic attack path is you identify a bankable target. This is quite easy to do. Then normally you get the firmware, and then it's your work to find vulnerability. I will say at least one, if you're lucky. By emulation, fusing, reverse, so all the techniques you can do to find a vulnerability, and then you develop an exploit based on this vulnerability. Normally, to develop an exploit, it's better to have a debug access. I mean, from my point of view, I prefer to have debug access. It's you can save a lot of time, and then you enjoy. It's cool. So typically on these products, based on EFM32 when you try to connect a debugger and see and read the flash to obtain the firmware and some stuff like that. And you can see these messages. This is the message from OpenOCD, a software debugger, which is linked to an hardware debugger, typically a G-Link or an ST-Link, for example. You will find these messages because the debugger will tell you it cannot find the MEM AP. We will see what it is later. And typically, you cannot access the debug interface. So why we cannot access the debug interface on this MCU? It's because, first, the vendor doesn't want to provide the firmware, of course, for free, because it can contain some, I will say, IP or secrets inside. Most of the time, the firmware can be encrypted also, when you can find that on their website. And what they use to set the platform is called the CRP. It's a code readout protection, and it's an hardware security mechanism, and it disables completely the debug interface. So it means you will not be able to debug the target and to play with once the project will be on the field. And this is present nowadays in most of the MCUs SoC with integrated flash you can find on the market. And it's quite painful because you cannot access the code or data stored in flash, so you cannot get the firmware, and you cannot start reverse on this. And as we know, if you don't have the firmware, you cannot reverse, so you cannot have the results. So we need to find a way to get this firmware and to have a full debug access on these platforms. So the target we focus on is the ARM debug access port, called also DIP. It's based on two different blocks, I will say. One external interface is called debug port, DP, and this is ARM proprietary. It's called SWDP for serial wire debug, and this is the equivalent of ARM for the JTAG, okay? And what is cool, it's they only use 2 pins, because like that they can reduce the number of trays on the PCB, and they can make minimization of the PCB like that. So normally, most of the time on ARM-based product, you will not find a JTAG, you will find SWD. And then once you have this DP, they will connect to a resource interface. It's called access port. And depending on the implementation, you will find different implementation. One simple is the main memory AP access port. And you can also find different implementation. HAB for the advanced bus, and also some other peripherals or control access port. So I link to the specification of ARM for that, in case you are interested. It's quite nice documentation. So here on this platform, we have what we call authentication access port. It prevents direct access to the flash and the RAM, but also to all the registers. So typically, you can do nothing on that. If this authentication access port is enabled, of course, when you read the datasheet of the platform, you will not find too much details because it's kind of security by obscurity. And if you look the diagram, this should be more called authorization mechanism than more authentication. But I mean, I don't do the datasheet, so. But nevertheless, from my point of view, it was never hacked so far. So it's why I decided to focus on, in order to be able to start reversing the different projects based on this platform. So how it works, it's quite simple. You have some log bits in Flash, identified at this address, so the source code were found in the IDE of the Silicon Labs tools. And this, typically, it's very simple. You have a word called a DLW. If this is set to F, you can access the debug. If it is different than 0xF, the debug is locked, and then you cannot access the debug and dump the memory, etc. So how do you activate that? You write 0x0 into this DLW word, and then you reset, and after that, the device will be protected. So, and this is really the same mechanism we saw on the NRF52 from Nordic. It's quite funny because Nordic is a competitor from Scilabs, and they use exactly the same mechanism. We can see the similarities. They call that AP protect, and it's mapped also in flash memory in dedicated registers. And if you write 00 in the end of this 32-bit registers, and then you enable the access port protection, and then you cannot disable without clearing all the memory flash and all the RAM. So, and here's the AP protect specification found in the Nordic. So it's quite similar. So my plan is quite simple. We were stuck at home this winter, so I decided to do a little bit of work. I decided, of course, to bypass this protection to reactivate all the debug capabilities on this EFM32. And why I'm confident to achieve this is because it's really similar than the NRF52. I did it on NRF52, so I say, okay, it should be simple. Take me one evening or not, one evening or two, and then I can profit. But we will see. Typically, I will use the same techniques. It's called voltage glitching in order to bypass the initialization of the authentication access port during the power on, and then like that I will connect just after that with the debugger, and normally I should have full debug access. So this was my previous method to bypass that on NRF52. I hope this will work on EFM32. So let's prepare a little bit. To do that, my preferred techniques is to buy a dev kit. So it costs me every time $100, fortunately. But yeah, why are you using a dev kit? In my opinion, it's because you have exposed interfaces. And most of the time, the debugger is already included. So you don't need even to solder some dedicated pins. So it's quite easy to work with the development kit. And generally, you have the reference design on the PCB of the dev kit is generally very close to the final product they will use, because the vendors, they don't care, and they just take the reference design and they apply for their product. And then, of course, once you have a dev kit, yeah, you can use for other projects. So it's always good to, I mean, it's not like throwing the money by the windows, I would say. So let's talk a little bit about the tools from the Scilabs. It's called the Simplicity Studio. It's their IDE, quite good IDE, I have to say. You create a project, it's very simple. You compile, then you flash the binary inside the dev kit. It works very well. I mean, I didn't have any trouble of that. And to enable the AAP, I installed a second tool called the Commander. It's a command line tool. And then using this command, you can lock the debug access. And using the second command, you can unlock the debug access. Unfortunately, of course, the unlock operation will erase all the flash memory contents. And then you cannot use that on a protected device, I would say. So of course, because we are going to use voltage glitching, it's interesting to take a look to the PCB in order to modify the hardware located near to the platform. And thanks to the IDE, of course, the schematics are present, so you will not have to reverse the PCB, so it's quite easy. And I decide, as you see on the schematics, to remove all the capacitors. So this is also I found that particularly easy and useful to remove capacitor, because once you will connect to the oscilloscope and to check the power consumptions, etc., you will have more information, because you will not have this low filter band, I will say, due to the capacitor. And your glitch also, once you will inject your glitch, will be sharper and more efficient. And you will be able to have a better repeatability, and you will have better results, in my opinion. But some other guys, they don't do they don't do capacitor removing, but this is their choice, I will say. So let's discuss about the power domain. It's quite a complex power domain in this little MCU, because first, they didn't give details in their datasheet, unfortunately. You have several domains based on digital domains, based on analog domains, etc. So, and as we can see on this diagram from their documentation, there are BOD, and this is for brownout detectors and also some filters. So maybe this can have an impact on the attack, on the glitching attack, but normally it's not a problem, I would say. But I'm quite optimistic guy, so we will see. Sometimes you can have a false ID. So let's time to hack now, and just talking about glitching for people which are not really focused on hardware. It's a very basic techniques called also called the voltage fault injections. It's very cheap to perform. You have a lot of public resources on internet, etc. I give only 2 links, but you will find a lot of different links. The goal is really to disrupt the power of the chip during critical operation, during a short amount of time, in order to disrupt the correct operation done by the platform. So typically what we can expect is to skip instructions, is to perform mutation of data, mutation of code. And nowadays it's very difficult to predict the fault model, because the CPU architecture are quite complex with different pipeline, with caches, etc. So sometimes you can have very surprising effects doing glitches on modern CPU. And you have also commercial tools. You can, but you can also do your own. It's very easy to do. So let's talk about power consumptions, because it's really important. So here you plug the scope, and what you will do is to monitor the power consumption. This is monitored once you reset the chip, and then you monitor all the VDD. So the channel number 1 is the VDD digital, and the second one is a little modification I did using an amplifier to really see the different patterns in the power consumption. So I was quite happy about the details I obtained. And why this step is quite important to do? It's because you have to focus on what you want to glitch, and you want to identify a particular process. And this particular process, I think I identify it on the red frame, and it's why on this particular process, approximately 50 microseconds, I will perform the glitching here, and only on this frame, on this red frame. Otherwise, it will take too much time to perform glitching on all the power consumptions you can imagine. So typically, what you do, it's called the side channel, a little bit side channel analysis, and then like that you can identify some particular process and focus on that only. So I started to do some glitching, and I remarked immediately it was not very successful, because every time I glitch the platform, it performs a glitch, and it performs a reset. And you can see on the red frames, the pattern are exactly the same. It means after the first red pattern, then you glitch, and the chip reset immediately, and then he start again. And this is not very good for glitching attacks, of course, because it means your glitch is not very successful. And this is due to these specific detectors called BOD, brownout detectors. They are analog detectors inside the chips, and they will monitor in real time the voltage and the state of the voltage. And if they detect a glitch or an overvoltage or an undervoltage, they will reset the chip immediately. And this is quite surprising. This brownout detector was quite effective. So I started by characterizing this brownout detector, and I have to say they were very well designed, because I didn't find any in protected range of operation. I did a different work on that, and for me it's one of the most I will say effective brownout detector right now on the market. So I have to say a special shout out to the designers from Scilabs for that. I also tried different glitching techniques by using different tools I designed, but unfortunately I was not able to bypass this detector and to reactivate the debug using voltage glitching. I was quite sad, but I think I need to find something else. But about hacking, it's to never give up and to try harder when you have some fails. It's very important to have this mindset, I will say. And so I decided to go to the next level. And the next level is electromagnetic fault injection. This is quite known in the electronic industry. Then the integrated circuits are very sensitive to electromagnetic waves due to electromagnetic compatibility, etc. So typically, the principle is to inject a strong electromagnetic pulse induced by a big current into the integrated circuits, and like that you will perturb and you will perform a glitch, but this glitch will not go through the brownout detectors, and they will go directly inside the chip. So I hope with this technique I maybe be able to reactivate and to perform the attack I want. It's a little bit like an electromagnetic bomb, but of course at a little scale. So I did some little bit of simulation, of course, and I was quite happy about the spatial resolution I obtained. I use a free software for that. I don't remember the name. I can give you later if you want. I started to design some probe, etc. And from what I read and from what I tried, it's the spatial resolution. It's really dependent on the probe design and on the field coupling, I will say. And this is quite complex because it requires a lot of mathematics behind, etc. So I will not detail too much that, and it's quite boring first. So, and of course, I look at the available commercial tools on the market. First, I have to say the electromagnetic fault injection is not a new technique. It's used during smart card security evaluations by a lot of security labs in Europe and all over the world. You can find a lot of academic research papers since 10 years now. And I look at different commercial solutions. So the first one was done by a Netherlands guy called Riscure, and it cost 20 key. So I say, okay. And the second one is from Neway, chip shooters, Colin O'Flynn, and it cost 3 key. So unfortunately, I don't want, or I cannot pay this price to break $5 chips. I can. I think it's obvious. So I will do my own. So I started to do some block diagram, etc. So typically I need a high voltage generator. Then I will store this high voltage power in a capacitor bank. Then I will use an electronics switch, and then I will inject this big amount of power inside a dedicated probe in order to generate an electromagnetic pulse. So I have some requirements. Of course, I would like to run that using a battery. I would like also to have some width, adjustable width, and an acceptable jitter. Otherwise, it's very difficult to have, I would say, repeatability. And of course, it has to be sufficiently powerful in order to perform fault injections. So my setup was this one, so you can recognize the dev kit. I use what I call a DER injector. It's was my first prototype at this time. It's based on disposable camera. I trick that by a TTL signal, so it's quite simple. It's ultra low cost, of course. Just a safety disclaimer about that. So because it's 750 volts, so I mean, I prefer to say that to people. It's quite can be dangerous. So if you are not sure, don't try that at home, because I mean I don't want to be responsible, and it's to be in good shape is better than breaking hardware security. So yeah, about probes, I did my own also. So I did some empirical tests, nothing very ingenious here. What I'm looking for, it's a very localized effects, because it's very important to have a very localized effect in order to not, I will say, be detected by these detectors, the BOD we saw before. I saw some people, they use XYZ in order to scan all the chips. Personally, I don't need, because it costs a lot. So I decided to do that by hand only. And at one moment, I was able to reactivate the debug interface, full unlock of the debug with a full read and write routines, and I was quite happy. You can see the breakpoints and the watch point are enumerated by the debugger, so it means everything is okay. And you will have full access to the debug, which is very cool to dump the firmware and to debug the target when you are developing exploit on that. And what is cool is you can dump the firmware, and then you erase the settings and you reflash again the firmware. It means you don't have to do the attack only once, and then you have the same device but with debug activated. So you don't have to do this fault injection all the time. So just a last scope view, you can see the glitch effect is very, very thin. I will say very, very sharp. I measured 50 nanoseconds. So, and for people who they want to reproduce that, the fault timing is indicated on this on this scope screenshot. So it will be you will be able to reproduce easily. So let's talk about the disclosure, which is a little bit painful every time with hardware vendors, I would say. They clearly mention no rewards on their disclosure policy, so I decided to post. And 4 days later, they were not very happy, but yeah, I mean, they just, I would say, publish a security advisory confirming my results. So you can see the CVS score, I mean, not rated by me. And what is quite nice, it's impact a lot of different products from their catalog. EFM32, of course, which was the one we were targeted, but also EFR32. This was a very cool result, I would say. And also their next generation based on Cortex-M33 were also impacted. So this was very cool. So yeah, about conclusion now. As we can see, the research on embedded devices requires at least to dump the firmware and to get access to debug interface most of the time. And this is more and more difficult every day because the vendors, they don't want anymore to let their interface open and to provide the firmware to their customer. So this work presents a new way to unlock the protection in order to reactivate this debug features on this large catalog of MCUs. It's funny because the vulnerability was present inside the different vendors, like Nordic, Scilabs, etc. So maybe other vendors can be impacted by this kind of attacks. And yeah, about EMFI, it's a very cool techniques. I will try to go to the market with these new tools available in 2022. I'm currently designing that, like I did in the past for voltage glitching, and I hope you will enjoy. Thank you.